Okay, so I will now. So we finished with the computation of the phase diagram for the simple theory like SU3 with n flavors. There are several levels of data here. On this column, we see the dimensions of each phase. On this part, we see the depiction of massless states in each phase. SU3 with some flavor, SU2, and no gauge. This is another copy of the same diagram where we now label the slices, the edges which connect between two nodes. One is of D type, minimal nilpotent orbit of type D, and the other is minimal nilpotent orbit. Okay, and it was pointed out that I switch between sides. So here I put the dimension, here I put the gauge group, so it's like here. But over here, I switch the dimensions to the right. Okay, so take a note of that. And here I wrote another characterization of those phases. Here the rank is 0, the rank is 2. So there are several characterizations we can use in order to label the phases. And each of those characterizations give a unique description of the phases in question. Okay, so we can either label them by dimension or by description, by quiver like here, or some other way which characterizes it. It's very similar to the phase diagram of water, where I have the three basic phases, solid, liquid, and gas. And each phase is characterized by some properties, like temperature, pressure. Here, instead of that, we denote the phases by properties that we use for the gauge theory description. But we could also characterize those phases through the geometric properties of these phases, because those are symplectic singularities. Let me now do, so this was the Higgs mechanism. Let's do a quiver subtraction. And for quiver subtraction, we will take two basic quivers. So this has n nodes and one flavor here, one here. The Coulomb branch, this quiver, is AN, which is what we said before. The minimal nilpotent orbit of SLN plus 1. We said here that the Coulomb branch, this quiver, is the Klein singularity. And we also computed that the Higgs branch is the minimal orbit. Now we have a different quiver. It's this form. The Coulomb branch is AN, and the Higgs branch, same quiver, is the Klein singularity, type A Zn plus 1. Okay? Both of those things you can compute. You have the tools to compute. To show that if you could take this quiver, compute the Coulomb branch, you'll find that it's the minimal orbit. You'll find the Hilbert series for the minimal orbit of SLN, and I gave you the formula, how it should look like. And the Higgs branch will be the A-type Klein singularity, which we also wrote down the formula in a previous. Okay, so all of those things are exercises. You should convince yourself that you know how to do exactly. A second quiver is the quiver of D type, which is going to be the following. So this is the ringing diagram for D. The total number of nodes is n, so number of screws, n minus 3. Now I can write down the Coulomb branch is Dn, which is the same as we found over here. The Higgs branch of this quiver is Dn. The Coulomb branch of this quiver is D. So I have two ways to construct the minimal nilpotent orbit, one as a Higgs branch and one as a Coulomb branch. And the Higgs branch of this quiver is the D-type Klein singularity, and we will denote it by Dn. Dn, dihedral group binary. Dihedral group of order for n minus 2. Any questions? Again, this is something which you could compute. You have all of the tools. If you have a problem in computing any of them, then I strongly recommend that you will compute it. You have a problem with any of them, come and talk to me, and let's see where is the problem.
Magnetic the industry says computer. Too difficult.
For what?
For
the Coulomb one?
Yeah.
Yeah, it's computable. To do it for the first few cases and then argue that it's forgery. You could do some tricks of summations. Again, there is this order of summation that you need to decide. Okay, so now let's compute the following quiver. So the Coulomb branch of this quiver This is the equivalent of from the family of SQCD.
Would you want to tell us a little bit about the balancing?
Yeah, we can talk about that. Yes. What?
He writes some numbers at the ranks. It's a certain rule. You can't put any.
Well, you can put as any numbers you wish. Question is what you compute.
Yeah.
So we can talk about balance. Remember that for a Coulomb branch, the quaternionic dimension is the rank of the gauge. In this case,
If it's multiplication.
well, if I give you a gauge group with the formulation that we gave, G can be any gauge group, including a product.
Right.
So the rank of a product is the sum of the rank. Right? So this is the correct definition for any gauge. So, for example, here, the quaternionic dimension is n, because I have n nodes of 1. That's the quaternionic dimension of the singularity an. And over here, we can count. So I have n minus 3 nodes of 2. So they will give me 2n minus 6. And I add 3 more. So 2n minus 3. And indeed, when we wrote down this Higgs branch, or this as the diagram, the dimension is 2n minus 3. The number of hypers minus the number of. Okay. Now, remember that yesterday when I gave this talk, I said that there are several ways to characterize the Coulomb branch. The first one is the dimension. So the dimension of the Coulomb branch is just the rank. The next level of information is the symmetry. We computed the symmetry for simple cases. We took U1 with n flavors and we said that the symmetry is U1 unless n is equal to 2 or 1, where the symmetry gets enhanced to S2. So how can we determine this? We look at define a notion of balance. This notion is a very natural notion if you think of brain systems which are used to construct those gauge theories. So it's really a balance in a notion of having some guys from here, some guys from here. If there are more from here, then it's imbalanced, and if they are equal, then it's fine. So define notion of balance by summing node numbers attached to a node and subtracting twice its node number. So we can do an exercise. If we look at this node, there are two nodes attached to it. And they have node numbers 1 and 1. So the sum is 2. If I subtract twice the node number, I get 0. So then I declare this node is balanced. This node is also balanced because it is attached to two nodes, left and right. Both of them 1, so the sum is 2 minus twice 1.
So if
All these nodes are balanced.
minus 2 is 0, 0 is balanced. Sum of the length of the neighboring nodes minus 2 should be 0.
Yeah, if final notion of balance, if let's call it B, if B is equal to 0, the node is balanced. If B is equal to minus 1, the node has negative balance or imbalance. And it could be positive.
Subtracting 2 times the rank of the term. The sentence
2 times. Thank you. Now do yeah. You have a better view.
no, what do you
I said it, but I didn't write.
Yeah, okay, sorry, I was.
No, but it's good that you tell me because I see that it's not written. Thank you. So now if you want to compute Hilbert series, the balance can be at most minus 1. It cannot be below that. If the balance is minus 2 or lower, then I will have some issues with the convergence of the Hilbert series. So I can only make the summation for cases where the balance is either minus 1 or above. Now, the global symmetry
So maybe the students won't, this is a rule, but there is a physical meaning to it. That's an arbitrary rule.
What?
The notion of a balance.
Is there a question? I don't hear a question.
Yeah, what is the physical?
I just explained it.
Okay.
So the global symmetry of the Coulomb branch for a large class of quivers can be computed by following condition, the subset of balanced nodes. They form the Dinkin diagram of the global symmetry. Then the remaining ones unbalanced nodes contribute U1 each. Okay, so if you look at this quiver, this node has one node attached to it of label 2. 2 minus twice 1 is 0, so it's balanced. Right. This is balanced. 2 plus 1 plus 1 is 4, twice. And these are all balanced. This is balanced, this is balanced, and this is balanced. So the balanced nodes form a Dinkin diagram of type D. And so the global symmetry on the Coulomb branch is of type D, SO2N, which is what we saw when we computed in this case, the minimal nilpotent orbit, or we gave a description in terms of matrices. Set of antisymmetric matrices of dimension 2n, which satisfy the conditions that the square is 0 and the rank is most. Any questions? Okay. So the dimension is over here 2n minus 3, and the global symmetry is dn or SO2. Okay. How about this one? So I didn't finish writing here. I want to choose that the number of nodes here is n minus 1. So what is the global symmetry? So first of all, let's compute the dimension. So the dimension of the Coulomb branch of this quiver is just the sum. So let's sum the numbers. We could also turn this one into flavor without any cost. So we will have 3 from here, 3 here, and 3 more. How many in total? N plus 1 times 3 plus 1. Sorry. And let's compute again. So you have n minus 5 of these guys. You agree?
Yeah, someone wants to know Can you please indicate which nodes are framing square nodes? Can't see properly, so I try to.
I chose a quiver where all nodes are gauged.
Right.
But it's up to you. You could engage anywhere you like. You could engage here, here, and here at 4 places at no cost. And you could also choose to engage in non-abelian. They are all equivalent.
Question?
Yes.
Then the knowledge of whatever the what
Over here, this one is flavor. But here they are all gauge. But I could choose, I could replace this by flavor without any cost. It's not going to change the theory.
Don't change.
In general, if I have a quiver, for any quiver, doesn't matter. Every edge has a start and an end. All of the edges in the quivers that we write, they have a start and an end. As a result, the sum of all U1s has no charged matter. Under it. So when I say the gauge group is a product. If I put labels K1, K2, and so on, the gauge group is product UKI, but there is no overall U1 where it's trivial. This is the gauge. So now there is an overall U1, I can choose it anywhere I like. I can make it, I can put it over here, put it over here. If you are familiar with brain systems, when I arrange brains in space-time, there is translation invariance. So translation invariance allows me to fix one of them to be the origin, and then all brains are measured with respect to it. This operation is similar to this overall U1, which is ungaged. And so for this reason, if you draw a quiver where all nodes are gauged, like in here, you leave the freedom of where to engage to a future study. It's anywhere you wish. Can be here, can be here. You could use it as the degree of freedom in your analysis.
But then the dimension of column was people is 3 times n minus 3 plus 2.
It's plus 1 because there's an overall U1 which is trivial.
Ah, okay.
So the sum of numbers is plus 2. But since an overall U1 is trivial, it's plus 1.
Like the set of.
That's This is a very critical point. It's very important, very physical. So we just need to understand it and use it. Right? Because in physics, the symmetry of translation invariance is very important. We use it many times. We use it to denote spontaneous symmetry breaking, translation invariance, and we use it when we learn about basics of quantum field theory, Poincare algebra, and so it's a very important symmetry. And here it shows up again in the form of this overall U1 that is has no charge under it. Okay, so the symmetry here is SO2n. Let's compute the symmetry over here. So we computed the dimension. What is the global symmetry? I have this node, which is not balanced. It has a positive imbalance. This has a positive imbalance. All other nodes are balanced. And how many nodes are there? N minus 1. Which Dynkin diagram do they form? A type. So the Dynkin diagram is of type A, N minus 1. So the global symmetry is SUN, and there is an additional U1 because of the extra nodes. One U1 is trivial, and the other one contributes another flavor seed. That's the second comment that I wrote here. The remaining unbalanced nodes contribute U1 each. Okay? Now let's look at the Higgs branch of SU3 with n flavors. What's the dimension? It's 3n minus 8. What's the global symmetry?
UN times U1.
Times U1, right? There is a baryon number. So the Higgs branch of this theory coincides in dimension and in global symmetry with the Coulomb branch of this theory.
Higgs branch of this is the same as the Coulomb branch.
Is it just a coincidence or there is?
Is it a coincidence?
But there is no principle in this story.
Well,
It is.
let's continue to compare. Now I will use a quiver subtraction. So if I look at this quiver, I notice that there is a subdiagram of this quiver, which is of D type. And I could replace this by a circle node without any cost. So there is a subdiagram which is of type D. What D is this? Let's count the number of nodes. So I have n minus nodes over here. The number of nodes without those two will be n minus 3. But this does have n minus 3 nodes. Yeah, so n minus 1 is the number from here to here. I remove this, I get n minus 3. This is precisely the number of nodes here. So Dn is a affine Dn is a sub diagram of the quiver. Let's call it quiver Q, so that we won't need to talk about it again. And now let's do a subtraction. I will align those two quivers. and I'll put 1 here, 2, 1, 2, 1, and 1. I align them and I subtract. So from the subtraction, what I will get is 1 here, 1 here, 1 here, and all the way 1 here, 1, and 1. And those two are this subtraction gives me 0. Next thing I'll do is to make sure the balance of those nodes of the top quiver are again the same balance as they were before. I keep the balance. So the subtraction keeps the balance. This node was balanced. Now the same node is no longer balanced. So I need to add some flavors in order to balance it. So let's put 1 here, and let's add balance over here. And since we started with n-1 nodes, I have here n-1 nodes. This one is a quiver we already saw. It's this quiver, and here there are n of them, here there are n-1, so the Coulomb branch of this quiver is a n-1. And the Coulomb branch of this quiver is dn, because I have n-3 here, which we wrote over here. So now let's write this information into a diagram. I start with this quiver here, Q. I subtract the dn. There is a problem with the counting.
You want to put it that?
Let's see why, right? So here there are n-1 nodes. If I count the number of threes, I have n-4. Sorry, n-1. Subtract 2 here, 2 here, so n-5 nodes. So here I have n-5 nodes. And this is here n-2.
There's a question in the audience. And you do rebalancing, could you add H nodes or flavor?
In general, what I would recommend is to do it for a quiver which is fully caged. And there's always a way to do that. So if I have a quiver with many framing nodes, let's say K1, K2, Kn, and I have framing here, framing here, framing here. This would be N1, N2, N, like that. I can always replace this by another quiver where I collect all of the flavor nodes into a single node. and then one node of 1 with edges that have multiplicities. Those two quivers are equivalent because if I engage this one, I will get this quiver. So if you are not sure, so as an answer to the question, if you are not sure what to do, make all nodes engage, and when you need to balance, you take this is equivalent to the circular quiver. One node with two edges of multiplicity 1. Right, so that's the circular quiver, which is also known as the affine A-type thinking diagram. Okay, so this is my answer to the question. So to summarize, we subtracted a dn minus 2. And we ended up with a n minus 1, which is precisely the same as the diagram as we had for the case of the Higgs branch of SU3 with n. Okay. So the two moduli spaces, Higgs bunch of these and the Coulomb bunch of these, agree in 3 properties so far. They agree with the dimension, they agree with the global symmetry on the nodes, both the UN factor and the non-abelian factor, and they agree on the other side. It remains to compute the Hilbert series and to show that they agree. That's the computation. I couldn't do it on the board, but it's an exercise that you can do and show. Once compute the Higgs bunch here, and once compute the Coulomb bunch here, show that you get the same Hilbert series. Furthermore, compute the Higgs bunch of these and the Coulomb bunch of this. And you will find that all properties agree: the dimension, the global symmetry, and the Hilbert series. If you have the patience, you could compute generators, relations, and all sorts. And this is an exercise, right? It's not going to be feasible to do it on the board, but it's a nice exercise to do.
The subtraction is somehow like fixated for the block.
So now it's very important comment. With the Higgs mechanism, we started at the bottom and we went up. With the quiver subtraction, we started at the top and we went down. So those are two, what is the right word for that? They are compatible. Complementary, yes, that's the word I was looking for. They are complementing each other. If you are powerful enough, I would suggest that you compute the Higgs bunch. So there is the property of inversion. The phase diagram of the Coulomb bunch of quiver Q And now I can talk about, this is for a large class of the quivers Q. Let's call it H, the phase diagram. Well, let's call it curly H. Here I'm going to erase. Satisfies the inversion where you reflect the diagram and replace a lowercase by capital case.
What is it?
So let's explain. So if I take this as a diagram,
What is this? This is curly H mean?
well, let's do it. So if I take this diagram, Bn minus 2, A n minus 1, now I'm going to reflect it. So I'll get a new diagram. And I replace a lowercase by capital. So A n minus 1, B minus 2, where A n minus 1 is the Klein singularity equal divided by Vn, and Dn is the Klein singularity C2 modular by Dn. It's what we said here. Same thing as here. It's denoted as Dn. So the claim is that the Coulomb branch of this theory is given by this Hasselhoff. And the Higgs branch of this theory, is characterized by this Hasselhoff. Then I get an H prime. H prime is the inversion plus replacement lowercase by capital. This is H, this is H prime.
So there's a question in the audience. As a special case, lowercase a1 is the same as uppercase a1, right?
Yes. Yeah, I mean, if you look at, so AN, we wrote it over here. AN is this, and this is AN. The Higgs branch is AN. AN and AN. If you pick N to be equals to 2, to 1, if you pick N equals to 1, then A1, the quiver becomes 1 and 2. So the Coulomb branch is equal to the Higgs branch. No question. Okay, so in general, now in order to proceed, we will have to introduce. So I picked this route of showing the Hasse diagrams because otherwise we will need to introduce brain systems, and with brain systems we will have quite a preparation to make. But the next step to do is to think about brain systems. So let me give an exercise. Compute the properties and by properties we mean dimension, global symmetry, and the Hasse diagram, phase diagram, and also Hilbert series of the quiver and now we will write 1, 2, 3, 4. 1, 4, 4. 3, 2, 1.
There's a question in the audience. Could an with n larger than 1 appear as slices produced by quiver subtraction?
Well, yesterday we saw such an example when we looked at the diagram for the affine Riemann.
Same question for Dn, C2 over T or C2 over O.
I'm not familiar with such cases. You'll have to incorporate. So for the type E, the answer is definitely no. For type D, you will need to introduce orthosymplectic quivers, and then you would use the same logic where you have an SPN theory with some number of layers. There's somebody advanced in the online.
It's a young child.
I see. Okay. So computes the property of this quiver, both for the heat punch and Coulomb. Can you find the dual quiver?
Again, the brain configurations of the dual quiver are related, I think.
In a very easy way, yes, but we need to introduce brain systems. So now, okay, we covered plenty of material today. It was way too much for students which are not comfortable with representation. So you tell me what you want to do.
So what you have to talk about brain systems at some point, and then
Yeah, if we will introduce brain systems,
Yeah.
we will be able to do slightly more,
and
especially if you want to understand magnetic fields.
right. So this is not yet.
Yeah, I mean, we now know how to take any quiver and in principle, we know how to compute the Higgs function and the Coulomb.
But we don't know yet about it. So,
Magnetic quivers are a tool which is introduced to compute difficult Higgs functions in cases nothing else works. But the way we compute magnetic quivers is only through brain systems.
and when
Some people, if you look at the works in the literature, some people computed magnetic quivers through guesswork, but this is very limited. We could try to do that with some collection of insights from classes theories, which I guess people here don't know.
that's another. But I think doing brain systems would be very good for the students here.
Okay.
And that's I think that's the work of Ami. It's the language.
That's the contribution,
Yeah.
not the creation.
Your grand academic venture will all about. So that would be good to read with. It is difficult to cover that now.
Yeah, I think it's going to be new material.
Right.
You tell me what you want to do. I'm happy to do it.
Yeah, we can do that, and I mean, yeah, that will also help with the the duality between Higgs and Coulomb particles, right? What they call
What they call what?
the mirror symmetry.
Yeah, I don't like this thing.
Sorry, I stopped saying the first thing. What do you call it?
It's more suitable to call use this electric magnetic
Electric.
duality, right? Electric construction and magnetic construction. Higgs bunch is using electric degrees of freedom. The Coulomb bunch is using magnetic degrees. That's the way we construct it. Right? It's weights, co-weights. So if you want, it's the Langland's duality. Right?
Yeah, you should have the
So we are doing part of the Langland's program. Right. So this notion that you say that the Higgs bunch of some quiver is the Coulomb bunch of another quiver, what you're really doing is that you once construct a moduli space using electric degrees of freedom, and you do the same moduli space using magnetic. Once it's the Higgs bunch, once it's a Coulomb. So it is really Langland's duality, because I mean, if you follow all of those things, right? In the Coulomb bunch, we use co-weights. In the Higgs bunch, we use the weights.
I think the picture would be complete with the brain configuration and the magnetic some basic development. Like a value, and then we can decide on Wednesday whether we want to continue doing more lectures the week after next week.
Yeah, but I would suggest to take spend some time
to
to
computation.
talk about computations.
Yes, I agree.
I think that the students should lead the conversation because I know all of this stuff. I don't know what stuff is not known.
Yeah, you should try to do some of the exercises. It's not, you just pick a very simple program. Try to compute all the 6 points and then you try to show the symplectic structure using the Poisson algebra. Not just holomorphic. Okay. So in order to show symplectic, you have to show that. So far, you are used to computing, generate equation, way of the gauging value operator split into representation of local symmetry. But these are all holomorphic functions. And addition of ingredient plus one yesterday.
Yeah, in fact, the Poisson bucket requires a discussion because for Higgs bunches, it goes through. It starts from the Poisson buckets for the matter fields, and the gauge invariants are polynomials in those. So the Poisson buckets just follow from the definition. But for the Coulomb branch, we have those objects, the monopole operators, for which we don't really know how to write down Poisson buckets. So there have been some works in the literature where there are proposals of what to do with the monopole operators. And the problem with those proposals is that they are good for very simple gauges. U1 with M flavors. If you start with U2 with M flavors, you get into a lot of. So there is a challenge to try and define Poisson brackets for quivers, large quivers, like these ones. And obviously, you want to get what you would get for the Higgs branch of the quiver. So that requires some work, and some work has been done in this direction, but there's still some more work.
They know a little, because I gave them the string theory like that, and half up to the middle. They know about the hard conservation, the basic fact of fast break configuration. Which brain and which brain.
You did fiber webs.
Yeah, and also which brain and
brain bending on brain.
Yeah, when have configuration. They know a little. Yeah, they know from my lectures.
Okay.
I mean, at least they were exposed to it.
Did you do some brain systems?
No.
Simple gauge fields?
Yeah, a little. I mean, I told them about how they take time. How the gauge would generate it. Something like that. Yeah, I mean, they know a little. They were exposed to such a fact. The mainly using mainly not really time. Okay, good. So
if you ask questions, I'm happy to answer.
Right. Okay. For the audience in Zoom, I think that's it for today, right? And we will continue with lecture number 5 on Wednesday next week at 4 o'clock Korean standard. Okay. So if there are questions in the Zoom meeting, please ask. And otherwise, we will meet each other on Wednesday next week. And next week on Thursday and Friday, we will have the workshop on symplectic singularities and field theory superchargers. So there is a separate workshop website. So if you want to attend online, please do register on the website. I will send a separate Zoom link, so it will be not the same Zoom. Okay. With that, let's finish the Zoom broadcast, and we will see each other next week.